Okay, so what we are going to discuss now is this problem, which is what is the direction of the induced current that we get by changing magnetic flux. Okay, changing not just magnetic field necessarily, but magnetic flux. So remember what we saw in the previous slides. We can induce current, we can induce an EMF by changing the magnetic flux. Changing the magnetic flux could be just by changing the magnetic field, but it can also be by changing the area or by changing the angle. This scenario here, where we change the angle, is the last problem that you're seeing here. Okay, for this problem, I'm going to make a demonstration, a separated video. So now let's just try to solve these first 4 cases. Okay, so let's see case A. What is going on here? We have this constant magnetic field, so we are not going to change the magnetic field, and the magnetic field is coming out of the page. Okay, so I'm going to make this drawing here, exactly the same there. We have this magnetic field, constant, not being touched, coming out of the page. Okay, initially we have our loop here. And what we are going to do, we are going to move the loop away from the region of the magnetic field. Okay, so we are going to come to this the next case where our magnetic field is still the same, not touched, right? But we moved our loop away. Okay, so with that we are going to induce a current because we have a change. Here in the top we had magnetic field. Now here we don't see the magnetic field through the loop. So we are going to induce a current to oppose this change. So opposing this change means I want to recover those magnetic field, those lines that I had before. And to have magnetic field coming out, what is going to be the direction of the current? The direction of the current will be counterclockwise. Okay, so this is the direction of the current induced. So the direction of this current, the answer for this problem is the direction of the current is counterclockwise. And how do I know that? Why is it counterclockwise? Well, so to understand that, you have to use your the first right hand rule. Now, put your thumb along the current and use your 4 fingers to see that this will mean magnetic field coming out of this loop. Okay, so this is problem A. So this problem A here. Let's see the next one, the problem B. Again, you see, in problem B, we have the magnetic field constant going into the page. We are not going to touch this magnetic field. Okay, what are we going to do now? We are going to change the area. The area was something like this. So you see many lines going through our loop. What we are going to do now is not change the magnetic field, but we are going to decrease this area. Okay, by decreasing the area, you see now that the number of lines going through the area, going through the loop, is much smaller. So we are going to induce a current to recover those many lines. Okay, so to get magnetic field going into the page, that means that the current that I will induce goes in this direction. In other words, our current, our induced current is, in this case, clockwise. Why clockwise? Again, we want the field to go into the page to oppose the change. Field into the page means current clockwise. Follow the current with your thumb and then use your 4 fingers to see that the 4 fingers are going into the page. Okay, let's see the next. So this was problem B. Let's see now problem C, this case here. What do we have? Well, in this case we have this loop, and we have, you see that this is a magnet. Okay, so we have a magnet that we only see the south pole of the magnet, so the north pole is going into the page. Okay, so what this magnet is telling us that we have magnetic field going into the page. Okay, so this is the south pole, that's what we see is the back of the magnet, and the front of the magnet is the north pole going into the page. Okay, and look, we are going to move this magnet closer and closer into the page. Okay, so in other words, we had initially the magnet far from our loop, so going into the page but far from our loop, not in the direction of the page but far from our loop, which means we had just few lines. As we put this magnet closer and closer, as we push this magnet towards this loop, we'll have more and more lines, stronger and stronger magnetic field. What we are going to do, the current that is going to be induced wants to oppose this change, wants to kill these additional lines that we are creating. So to kill these additional lines that we are creating, now we want magnetic field coming out. Coming out means that the induced current will be in this direction, will be counterclockwise. Again, how do I know that the current is counterclockwise? Use your the first right-hand rule. Thumb following the current and uh, the four fingers coming out of the loop, so magnetic field coming out of the loop. Okay, so this was problem C. Last one that we are going to see in this lecture is going to be the D. What is the D? We have our loop, we have a magnet north and south, which means what is the direction of the magnetic field? Parallel to the loop. Okay, and what we are going to do, we are going to bring this magnet closer and closer. Well, what is going to happen? Nothing. In this case, we are not changing the flux, the magnetic flux, because remember, the magnetic flux depends on the angle, depends on the magnetic field, depends on the area, and depends on the angle, this angle theta. This angle theta in this case is 90 degrees. No matter where we are, close or far from the loop, the angle is 90 degrees. So the initial magnetic flux in this case is 0 and the final magnetic flux is 0. So I don't have a change in magnetic flux. I do not have any current. Okay, so what we saw, the first one counterclockwise, the second one clockwise, this one counterclockwise, and this one no current. Now this next case here, I'm going to show to you in a separated video, because then I can move the loop and make it probably easier for you to see what is going on.